Okay, so first let me thank the organizers for the opportunity to speak. And second, everything that I'm going to say is joint with George Pappas. Okay, so the title promises both unitary and orthogonal Shimura varieties. So I'll start with the unitary ones. So let's fix a quadratic imaginary field. And some non-negative integers s and t. And then let m st c, this is going to be the moduli space of abelian varieties A over C with an action of the ring of integers in our quadratic imaginary field and a principal polarization. A to A check. And I want the action of OK and the polarization to satisfy the following two conditions. So for all alpha and OK, okay, so first I just want the action of OK and the polarization to be compatible in some reasonable sense. So what that means is that for any alpha and OK, I have a commutative diagram like that. And so far, the integers s and t haven't appeared anywhere in the definition. So now s and t are describing the way that OK acts on the Lie algebra of the abelian variety. So this is the first condition. The second condition is that the determinant of x minus alpha acting on the Lie algebra of A is x minus alpha to the s times x minus alpha bar to the t. Signature condition. So this moduli space is smooth of dimension s times t. And in fact, you can say much more. So for those who have never seen these things before, there's a very pretty explicit uniformization of this by a Hermitian domain. So you can write m S, T, C as a disjoint union over some L of some Grassmannian DL modulo aught L, where what is this stuff? So the L runs over all self-dual Hermitian OK modules of signature ST. Aught L is just the automorphism group of this lattice with its Hermitian form. And DL is the set of all, I mean, you have some Hermitian OK module of signature ST, so you can tensor with the complex numbers, and over the complex numbers, your Hermitian space has a decomposition into a positive definite space of dimension S and negative definite space of dimension T. And you just look at the parameter space of all such decompositions. So D of L is the set of all positive, definite, S-dimensional subspaces of L tensored over OK with C. Okay. So that's a perfectly nice complex Shimura variety. I'm not going to use this complex uniformization because I want to go in the other direction and talk about the reduction mod P. So this Shimura variety has an integral model, well, let's say canonical model, over its reflex field, which is usually K, but is sometimes Q. So it's K if S is different from T, and Q if S is equal to T. And if I fix a prime P unramified in K, then we get a smooth integral model over either OK localized at P or Z localized at P, depending on the signature. So you get the integral model just by replacing C by your favorite scheme over this space. Just this verbatim the same moduli problem. OK, and so once you have this integral model, you can reduce it and try to figure out what the special fiber looks like. So the goal is to understand the special fiber, which is a little bit too ambitious all in one shot. So we set our sights lower and just try to understand inside of it the supersingular locus. Okay? So it's the moduli, the closed subvariety inside of here of points where your abelian S plus T fold is supersingular, meaning isogenous to a product of supersingular elliptic curves. OK, so what do we know about this? So there's one case where we know essentially everything. So there's a theorem of Pollard and Pollard-Vadehorn that tells us essentially everything about the supersingular locus in the special case where either S or T is equal to 1. So here's a theorem. So suppose that in fact P is inert. Then, OK, their theorem tells us essentially everything about the supersingular locus. I'm not going to tell you everything about the supersingular locus that their theorem tells us. But the highlights look roughly like this. So first of all, so here we're taking ST to be n minus 1 comma 1. Well, OK, so first of all, they compute the dimension of the supersingular locus. So somehow maybe the least exciting part. And it's, I mean, the whole Shimura variety has dimension, OK, the product, which is just n minus 1. The supersingular locus is roughly half as big. So you take n minus 1 over 2, and then you take the floor of that. But they really give a kind of global result that tells you exactly what the supersingular locus looks like. And it looks like the following. So it's some union over some indexing set of some other things. Okay. So to be a little bit more explicit, so I won't say much about the indexing set. I'll tell you more about what these x lambdas are. So each x lambda is some locally closed subvariety of the supersingular locus. So it has the form of some open subset intersected with a closed subset. It's a stratification of the supersingular locus. So if you take one of these things and take its closure, it's a union of other of those things in the union. So x lambda bar is a union of other x lambda primes and then the part that really has some meat to it. They really say exactly what these x lambdas are. I'm not going to tell you exactly what they are, except to say that each x lambda is something described entirely in linear algebraic terms. So each x lambda is a generalized Deligne-Lustig variety for a unitary group for the extension fp squared over fp. So what does that mean? So a unitary group, let's say G, i.e. X lambda, is a moduli space of certain parabolic subgroups in G or P inside of the base change of G to an algebraic closure, such that if you take this parabolic subgroup, apply Frobenius to it to get another parabolic subgroup, those two parabolic subgroups should be in some sort of fixed relative position. So a moduli space of parabolics such that P and Frobenius of P are in fixed relative position. And I'm not going to elaborate on that, except later on I'm going to give another example of a Deligne-Lustig variety. And in the example that I give, the notion of fixed relative position will be much clearer somehow. But for the moment, let me just leave it at that. Okay. Good. And then, well, here's an open problem. If that's signature n minus 1 comma 1, well, what about all the other signatures? So open problem. So we'll come back to that in a minute. But let's talk now about the orthogonal Shimura varieties. So I think you'll hear a lot more about these in Fabrizio's talk this afternoon. So I'm just going to say the bare minimum that I need to say. So let V be a quadratic space over Q of signature n comma 2. So in the unitary case, there are Shimura varieties for every signature. In the orthogonal case, you only get Shimura varieties associated to quadratic spaces of signature n comma 2. Then there's a, okay, so everybody knows that the special orthogonal group is not simply connected. It has the spin double cover. So we want to look at something slightly more complicated. There's a G-spin cover. And I'm not going to say anything about it except for two things. One, it's an extension of the special orthogonal group by the multiplicative group. I'm going to call it G. And the most direct, the way of defining it to me that makes the most sense is just by definition, this appears, it begins life, as you take the Clifford algebra of the quadratic space V, and then you take its unit group, and this G-spin is by definition some subgroup of that. OK. So if we want a Shimura variety, we need Shimura datum. This will be my group. And now I have to give you some Hermitian domain on which that acts. And my Hermitian domain is this. So D is going to be so a subset of projective space over V. I'm going to take the set of all Z in the complexification -0 such that Z is an isotropic vector. And the pairing of Z and Z bar is negative, modulo C cross. So it's an open subset of a quadric in projective space. And then the group G acts on this domain through the map from G into the special orthogonal group. And so we get a Shimura variety. That I'll call, what do I want to call it? X. Not very creative. X is G of Q mod D cross G of the finite ideals modulo some compact open. Okay. It is typically not a moduli space of abelian varieties. But in some ways, it behaves like it does. It's not of PEL type, but it's of Hodge type, which means you can embed it into a moduli space of abelian varieties and then use that to study it. So what you do is this G is a subgroup of the multiplicative group of this Clifford algebra. And so G acts by left multiplication on the Clifford algebra. So that gives you a natural representation of this group G. And it turns out you can put a symplectic form on the Clifford algebra in such a way that that representation gives you a map from G into GSP of the symplectic form. So you let W be the Clifford algebra with G acting by left multiplication. You get a map from G into GSP W for some symplectic form. And then that map from G into here on the level of Shimura varieties gives you a map from G into a Siegel modular variety. And then you can take the universal abelian variety over that Siegel modular variety, pull it back to X. And hence an abelian variety. A over X of dimension pretty big. I mean, its homology is the Clifford algebra, which is 2 to the n plus 2 dimensional. And so it has dimension 2 to the n plus 1. So it's a pretty big abelian variety. But that's fine. And I mean, somehow morally, or at least to sort of zero with order, you should think of A as being some sort of universal abelian variety over X. Although it's difficult to pin down. I mean, clearly when you, it's not how you spell Siegel. Is it? How do you spell Siegel? It's not important. Clearly when you take the universal abelian variety here and restrict it to X, it acquires some additional wonderful properties. It's very difficult to pin down and enumerate exactly what those wonderful properties are. They are truly wonderful, but it's somehow impossible to spell them out. I mean, because X is not a PEL Shimura variety. OK, now, under some reasonable hypotheses, a theorem of Kissen gives an integral model of the whole package, the Shimura variety and the abelian variety over it. So the reasonable hypotheses are going to be, assume there exists a ZP lattice L inside of V such that the determinant is a unit. Which basically just means that G has a hyperspecial subgroup at P. Then a theorem of Kissen, maybe also Adrian Vaziou. Maybe I don't want to get into the question. And Vaziou, that's not how you spell Vaziou. Okay. The whole thing, A over X, has a smooth model. Over Z localized at P. And if you have an integral model, you can reduce the thing mod P and ask for the locus of points where A is supersingular. So hence, X P bar has a well-defined supersingular locus. It's by definition where A is supersingular. So I'm going to tell you what we think that is. So I don't know exactly what to call this. I mean, I'll say conservatively that it's a conjecture. I mean, more optimistically, it's a future theorem. It's work in progress. We'll be able to prove this. Give us a little more time. Conjecture. OK, here's what the supersingular locus is. So first, I'm going to define an integer d, which is roughly half of n. What does roughly half of n mean? It's n plus 1 over 2 if n is odd. It's n over 2 if n is even, and minus 1 to the n over 2 times the determinant of that lattice L is congruent to a square mod P. And it's 1 more than that if n is even, and the same thing is not a square. Quite a workout. OK, and now what I claim is that I can describe the supersingular locus in terms of some purely linear algebraic construction. So what do? OK, take that integer d. There are 2 quadratic spaces of dimension 2d over fp. Right? Of those 2 quadratic spaces of dimension 2d, one of them admits a Lagrangian subspace, an isotropic subspace of dimension d, and the other one doesn't. Take the one that doesn't. So let omega d be the non-split quadratic space of dimension 2d over fp. Okay, so it does not admit a Lagrangian. Now, take that. OK, so then every irreducible component of the supersingular locus is isomorphic to the following object. So this omega d has no Lagrangian subspaces. But of course, if you base change to an algebraic closure, it does. So I'm going to look at the set of all Lagrangians L in omega d tensor fp bar, such that, OK, if I take a Lagrangian and apply the Frobenius to it, I have to get something different. And what I want to insist is that when I apply the Frobenius to it, I get something that is as close to the thing I started with as it can possibly be, given the constraint that it has to be different. Meaning, Lagrangians L such that the dimension of L plus the Frobenius of L mod L is 1. So L and its Frobenius overlap as much as they possibly can. This is an example of a generalized Deligne-Lustig variety, right? Because the parabolic subgroups of a special orthogonal group are the stabilizers of isotropic flags. A Lagrangian is just a particularly simple kind of isotropic flag. So these Lagrangians, their stabilizers are parabolic subgroups. So I'm looking at parabolic subgroups such that it and its Frobenius are in some fixed relative position, where fixed relative position means as close as they can possibly be. Except every irreducible one, there's one catch, which is that this is not actually irreducible. This is, in fact, disconnected. It has two connected components, and the two components are isomorphic. So if I put a 1/2, then it's clear what I mean. OK? OK, so that's the conjecture. So let's look at some special cases. So I claim that, this is true for n equals 1, 2, 3, and 4. And the reason, so for n equals 1, 2, 3, and 4, these orthogonal Shimura varieties actually turn out to be of PEL type because of certain exceptional isomorphisms, which makes them easier to study. So let's just go through these special cases and figure out what's going on. So if n equals 1, yeah, what's up?
Right. So here, do you expect stratification like all of that?
Oh, yes. I mean, this is somehow the weak form of the conjecture. The strong form tells you everything else you would want to know about this, like how the components intersect and the stratification. Yeah. I mean, this is just the simplest statement. Yeah. I mean, for example, when you intersect two irreducible components, their intersection is exactly of the same type, but for a lower value of d. I mean, they're nice sort of hereditary properties. OK, when n equals 1, at least on the level of real Lie algebras, SO12 is the same as SL2. And so we're really talking about modular curves and Shimura curves. So X is a modular curve. OK, you go and you take n equals 1. N is odd. 1 plus 1 over 2 is 1. So d equals 1. You go take d equals 1 here. We're looking at the non-split quadratic space of dimension 2. When you base change to the algebraic closure, you just get a hyperbolic plane. Hyperbolic plane has exactly 2 isotropic lines, and both of them satisfy this property. So this is 2 points. We take one of them. It says the supersingular locus of a modular curve is a bunch of points. It's true. Check. OK. N equals 2. SO22 on the level of real Lie algebras is SL2 cross SL2, which means we're talking about Hilbert modular surfaces and twisted variants, quaternionic Shimura surfaces. So now X is a Hilbert modular surface. For some real quadratic field, F, which appears as something like the center of the even Clifford algebra. And OK, so now n is even. And you can see when n is even, there are 2 cases. So what's going on here? So what's going on is that, so the existence of this lattice is a kind of unramifiedness condition. So our prime P is going to be unramified in F, but there are 2 cases now. It could be split or inert. And that's why we're seeing the 2 cases here. So if P splits in F, then that's the case where D is 1. And the supersingular locus is a union of points. This was also D equals 1. And that's true if you just think about it for a little while. You can convince yourself that the supersingular locus is zero-dimensional. That's not terribly interesting. What's more interesting is if P is inert in F. That's the case where D equals 2. You go and you work out what this is when D equals 2. It's a little bit more complicated, but the answer in the end is you get P1. And so it says that the supersingular locus is a union of P1s, which is great. Sadly, this was already known. This is the PhD thesis of Helmut Stamm. So that's already a theorem. But at least the good news is that the conjecture is true. The bad news is that it's not a new theorem. OK, so we move on, hoping against all hope that we can prove something that somebody didn't know before. N equals 3. I'm going to erase this. It's in my way. OK, N equals 3. Let's see. SO32. SO32. Where have we seen that before? SO32. Again, on the level of real Lie algebras, SO32 is the same as the 4x4 symplectic group. So now our Shimura variety is just the moduli space of polarized abelian surfaces. You take n equals 3 in that recipe. I erased the recipe. There's some vestige of it. N equals 3 for D equals 2. We already saw D equals 2. And the supersingular locus is again a union of P1s. This was also already known. This is a theorem of Katsura and Ort. OK, we keep our fingers crossed. N equals 4. SO42, that's SU22. We win, right? OK, so now what? So X is, well, it's just M22. Okay, for some quadratic imaginary field. Okay. If P is split in K, then again, D is 2. And the supersingular locus is a union of P1s. But if P is inert, then we get something else that we haven't yet seen. So here's the theorem. Assume P is inert in K, then M22 supersingular. Well, let's say every irreducible component of this is, so you go and look at that weird space of Lagrangians when now D equals 3. And, well, it's low enough dimension that you can just sort of figure out by hand what that space is. It turns out to be the Fermat hypersurface. So it's the smooth projective surface x1 to the p plus 1 plus x2 to the p plus 1 plus x3 to the p plus 1 plus x4 to the p plus 1 is equal to 0. It's just that when D equals 3. But you'll see in the proof that in the proof, this is actually the thing that appears. This is just some calculation from that. OK, so before I begin sketching the proof, let me say a few things. Okay, any sensible person would ask, well, can you keep going? N equals 5 is, sadly, as far as I know, nothing special at all. N equals 6 is actually a PEL Shimura variety again. SO62 is something like a symplectic group over a definite quaternion algebra. So it's some moduli space of abelian varieties with an action of a definite quaternion algebra. And then that's it for PEL type. Then something cool happens when you get, there's nothing interesting, 6, 7, 8, 9, 10, nothing interesting, until you hit n equals 19. And then, of course, as everybody knows, the SO19-2 Shimura variety is actually the moduli space of polarized K3 surfaces. So if you take n equals 19, this is a conjecture about what the supersingular locus of polarized K3 surfaces looks like. And as far as I know, there's no such statement or conjecture in the literature. It is known what the dimension of the moduli of supersingular K3 surfaces is. This was computed by Michael Artin. He got 9. And OK, at least the dimension agrees with this. But I mean, this is a conjecture of what the actual global structure of the supersingular locus looks like, which I think is pretty cool. It's possible that n equals 19 is the most interesting case. OK. So I'm going to spend the rest of the talk sketching the proof of this. I mean, this is easier than the general orthogonal case, precisely because this is actually a moduli space of abelian varieties. So, sketch of the proof. The proof looks exactly like the Fallard-Vadehorn proof in the UN-1, case. You start out exactly the same. You keep doing it until it doesn't work. Then you use one stupid trick, and then everything works OK again. So the beginning is exactly the same. So let's fix a base point. Fix a base point that I'm going to call bold A. So some point in the supersingular locus of our Shimura variety. And then from the base point, you can construct the Rappaport-Zink space for the Shimura variety. So you let G be its p-divisible group. Okay. And then I'm going to let script M be the reduced scheme underlying the associated Rappaport-Zink space. So what that means is that, I mean, I'm not going to define M, but I'll just tell you what its geometric points look like. So it's a moduli space of pairs consisting of p-divisible groups together with a quasi-isogeny to our base point. So script M, fp bar, is the set of all pairs G comma rho, in which G is a p-divisible group over fp bar with an action of OK and a principal polarization. I mean, compatible with the OK action in the same sense that it was in the Shimura variety. And rho is a quasi-isogeny to our base point. So an OK linear quasi-isogeny. So it means it's a map. An OK linear map from G to G with P inverted. Identifying the polarizations up to QP cross scaling. And then the uniformization theorem of Rappaport and Zink tells us that our supersingular locus is some disjoint union of quotients of this thing. So disjoint union of some m mod gamma i's, where gamma i's are some discrete groups acting on this. I mean, the gamma i's are discrete subgroups of the automorphism group of the base point. But to prove this theorem about the irreducible components of the supersingular locus, it's enough to prove the same theorem for the irreducible components of M. And so that's what we'll work with. OK, so the reason it's easier to work with the Rappaport-Zink space is that we can describe p-divisible groups in terms of Dieudonné modules and convert this. I mean, we've gone from abelian varieties to p-divisible groups. Now we'll go to, instead of a moduli space of p-divisible groups, a sort of moduli space of Dieudonné modules, roughly. So let bold D be the Dieudonné module of the base point. So it's a module over the Witt ring. Of what? Of rank 8. And it has an action of Frobenius and an action of Verschiebung, satisfying the usual relations. And, right. And the polarization on our base point induces a Hermitian form on D. So the polarization induces, well, OK. It also has an OK action. And the polarization induces a Hermitian pairing. D cross D into OK, tensored with the Witt ring that I'll call Langle-Wrangle. Okay. So that's the structure on the base point. If I take any point on the Rappaport-Zink space, then that point is also corresponds to some Dieudonné module with the same structure on it. And then we can use the quasi-isogeny rho to relate the Dieudonné module of our point with the Dieudonné module of the base point in sort of the usual way. So for any point G rho, we get a Dieudonné module D and rho lets us realize this Dieudonné module as a submodule of the base point Dieudonné module, at least after inverting P. So rho of D is contained in the Dieudonné module of the base point after inverting P. And so as you let G and rho vary over all points in the Rappaport-Zink space, you get some family of lattices inside of here. And we want to write down exactly what this family of lattices is. So here's a definition. So a Dieudonné lattice D inside of the base point with P inverted is a W lattice such that, OK, so I mean, if I take this rho of D inside of here, what sort of properties does it have to have? Well, my p-divisible group had an action of OK on it, and this map rho was OK linear. So this has to be stable under the action of OK on here. So D is OK stable. my D here was itself a Dieudonné module. And so when I realize it inside of this isocrystal, it has to be a sub-Dieudonné module, which just means this has to be stable under F and V. And the stability under F and V, you can just say that P D is contained in V D is contained in D. That in particular, that also implies that it's stable under F using the relation between F and V, using this. And 3, D was itself, well, G was endowed with a principal polarization, which means that D also has a self-dual Hermitian form on it. And this rho identifies the polarizations up to scaling, which means this lattice should be self-dual up to scaling. So D check is equal to some multiple of D for some C and Z, where this means dual lattice relative to the Hermitian form. And this characterizes exactly the lattices that you can get out of this procedure. So there's a bijection from the points of the Rappaport-Zink space to the set of all Dieudonné lattices. The bijection is G goes to rho of D. OK, which looks great. I mean, it looks like we've gone from something kind of abstract to something really concrete. It's just a collection of lattices. The problem is that this isn't. The problem is this. I mean, so far I have not used anywhere the hypothesis that our signature is 2, 2. Right? This works. Everything I've said works for any signature. The problem is you get down to this point. We're trying to figure out the algebro-geometric structure on this. Like, what do its irreducible components look like? The right-hand side, if somebody walked up to you on the street and handed you that collection of lattices, you would have no idea that they came as the points of an algebraic variety. This has no a priori structure on it other than set. And so if you want to figure out anything about the algebro-geometric structure here, you have to find some other structure from algebraic geometry on here, something beyond just set. And if you do this for arbitrary signature, you can just stare at this collection of lattices and never see anything more than set. In signature 2, 2, you can continue to stare at this collection of lattices and never see anything other than a set. And the whole trick, the only new idea, is we're supposed to be, I mean, this is supposed to somehow come from the fact that SO42 is the same as SU22. And all of this is really on the Hermitian side. It lives over here. But somewhere, lurking in the shadows, is some sort of quadratic space of rank 6 that we haven't really seen yet. So now we're going to figure out what that mysterious rank 6 quadratic space is, and then transfer this to a collection of lattices in that quadratic space. And then everything will be clear. So here's what you do. I mean, you have to figure out sort of what this exceptional isomorphism is. OK, so where are we going to get a quadratic space from? So first, note the following. There's a map from the exterior square of D. So this is the exterior square as an OK tensor W module into the endomorphisms of D, which is defined as follows. A wedge B, I realize as an endomorphism by A wedge B of X is, I use the Hermitian pairing. It's A X times B minus B X times A. So my exterior square now appears as a collection of endomorphisms. The exterior square has an involution on it. It's the Hodge star operator. So you have to fix a tensor, omega, in the top exterior power, such that, OK, so this exterior power inherits an operator F and a Hermitian form from the operator and Hermitian form on D. And I want F omega to be P squared times omega. And I want the Hermitian norm of omega to be, I forget, 1. Seems reasonable. It's not unique, but there always is one. And as soon as you pick one, that induces a Hodge star operator on the exterior square as follows. So there's a Hodge star operator star from wedge square d to wedge square d defined by. So if I take x and y, so these are now going to be in the exterior square, I define y star by telling you what it wedges against for every x. So this is in the exterior fourth power. Y star is defined by, this should be equal to the pairing of x and y times omega. That defines an involution. And now, the space of special endomorphisms of the base point D is defined to be the set of all x in the exterior square such that x is fixed by the Hodge star operator. And that's now sitting inside of, that's some collection of endomorphisms of the Dieudonné module. W module endomorphisms, anyway. And what's amazing is that this is a rank 6 W module with a quadratic form. Q, which is just you take, it turns out if you take any such x, view it as an endomorphism, and square it, you always get a scalar. And that defines a quadratic form. And not only is it a rank 6 quadratic space over W, from the Frobenius on D, this inherits an isocrystal structure. And it's an isocrystal of slope 0. So it has an operator phi, at least after you invert P, defined by, you take your x, you think of it as an endomorphism, and then you conjugate by Frobenius. And then if you take the fixed points for that operator, this is a rank 6 QP quadratic space. And it's actually sitting inside of the Frobenius. I mean, the condition that a special endomorphism here be fixed by phi is exactly saying is that it commutes with the Frobenius operator. And endomorphisms of the Dieudonné module that commute with the Frobenius operator, these are just quasi-endomorphisms of the p-divisible group. So end G, 1 on P. So I've just constructed some distinguished subspace of the endomorphisms of the base point. But what subspace I get, it's not quite canonical. It depends on this choice of tensor. But you make a choice, and you get a subspace. And now, we take this family of Dieudonné lattices, and we convert it into a family of lattices inside of L with P inverted. Okay? And that works as follows. So there are going to be 3 flavors of lattices. I've told you the first flavor, Dieudonné lattices. The second flavor are going to be called, rather uncreatively, special lattices, because they live in the space of special endomorphisms. So definition, a special lattice is a W lattice. L inside of this slope 0 isocrystal such that, so 1, it should be self-dual relative to the quadratic form Q. And 2, what's property 2? Oh, right. The one that should look very familiar. So I'm sitting inside this slope 0 isocrystal. I want a lattice with the property that when you shift it by the operator phi, it's very, very close to what you started with. So L plus phi of L mod L is isomorphic as a W module to W mod PW. It turns out that this L adjoin 1 on P has no phi invariant lattices. So this is as close together as L and phi of L can possibly be. And there's a bijection from, OK, so we have the bijection that we started with. This is in bijection with the set of Dieudonné lattices. The Dieudonné lattices are in bijection with the set of special lattices as follows. I take a D. I take it to, my special lattice is supposed to be inside of L adjoin 1 over P. L adjoin 1 over P is a collection of endomorphisms of D adjoin 1 on P. So I could look at all elements in here that stabilize the lattice D. And that would give me a lattice in here. It turns out you do something slightly different. You send it to L, which is the set of all X, set of all special endomorphisms, not that stabilize D, but that stabilize VD. And that actually gives you a bijection. And so now we just have a different family of lattices. Okay? But I claim, some of the reason that this family of lattices is easier to understand is precisely because somehow in all this we switched from a slope 1/2 isocrystal to a slope 0 isocrystal. And what we can do is, somewhere in this family of special lattices, we're looking for, say, irreducible components of this. So we want like subfamilies that look like they might form an irreducible variety. How would you group special lattices together in clumps? Well, they're living inside of this W module, but that W module actually comes to us from a QP vector space. So you can do something like fix a lattice inside this QP vector space, and look at all of the lattices in here that are somehow close to that thing. All right? And that's essentially how we're going to find the irreducible components here. So we want to approximate special lattices by lattices in this QP vector space. So let's give those a name. So a vertex lattice is a ZP lattice, lambda, inside of our QP quadratic space. Such that P lambda is contained in, the dual of lambda is contained in lambda. And these vertex lattices are almost going to index the irreducible components of the Rappaport-Zink space. Right. So for each one of these vertex lattices lambda, this lambda is sitting inside of L 1 on P fixed by Frobenius, which is sitting inside of the endomorphisms of our base point. Join 1 on P. And remember, for each G row in the Rappaport-Zink space, this row determines an isomorphism between end G 1 on P and end of the base point. So actually, I guess I want lambda check here. So I can think of lambda check as sitting inside of here. Okay. So now I'm going to define a sort of subchunk determined by lambda. It's going to be the set of all G rho such that these endomorphisms are actually integral. That's a closed subvariety for every vertex lattice. Okay? And so we've got, just by definition, this is sitting inside of the whole Rappaport zinc space. This is in bijection with the set of all special lattices. What is this in terms of lattices? This is just the set of all special L such that, well, the condition is essentially that lambda check is contained in L. But lambda check is a ZP lattice, so I'll tensor it with the Witt vectors, and it'll still be inside of L, and that'll be inside of lambda W. So this M lambda, if the whole Rappaport zinc space is the set of all special lattices, this M lambda, these are the special lattices that are just stuck between lambda check and lambda. But what is that? I mean, to give a lattice between here and here, think about what this is saying. That's the same as giving a subspace of lambda mod lambda check tensored with FP bar. Ignore that. I mean, all I'm giving is a subspace in the quotient, right? Now, you just unwind what special means. So special meant that L was self-dual, first of all. The self-dual condition just means that this subspace is isotropic. Well, not only isotropic, but maximal isotropic. L is Lagrangian. And the other condition was that, which says exactly that the dimension of L plus the Frobenius of L mod L is 1. Okay. So, oh, look at that, right on time. So I've just found a chunk that looks exactly like the thing I described at the beginning. You just have to run through what the possible lambdas are. So these vertex lattices themselves come in 3 flavors. So the dimension of lambda mod lambda check is either 2, 4, or 6. Okay? If 2, then M lambda is a point. If 4, then M lambda is P1. And if 6, then M lambda is that Fermat surface that I wrote down in the theorem. And so what you do is check that, well, let me just say this. I'm already 2 minutes over, but I'm going to write this anyway. So fact, the M lambda with lambda mod lambda check of dimension 6 are enough to cover the whole thing. Okay? Hence, every irreducible component is one of these guys. But there's, so that actually just, that proves the theorem that I said. There's one more thing that I'll point out, which is you can also read off from this how the irreducible components intersect. So m lambda intersect m lambda prime. Sorry, m lambda intersect m lambda prime is m lambda intersect lambda prime if lambda intersect lambda prime is a vertex lattice. And it's empty otherwise. So, two irreducible components intersect either along, well, they could have empty intersection, but if they intersect, if the intersection is non-empty, you have to get one of these things. So if you take two irreducible components, they intersect either at a point or along a P1. So bonus information. Okay, I'll stop there. Thanks. I don't know. I haven't worked it out. I mean, no, it should be higher dimension, probably three-dimensional or something. But in the 6-2 case, or in the yes, that's right. That's right. Well, no, there's going to be a real quadratic field involved, and there'll be one answer when P is split in the field and one when P is inert. When P is split, you should probably get this again. You should get, and then when P is inert, you'll get something one higher dimension that I haven't worked out.